All right, good morning, everybody. Welcome back to CS 125. It's a beautiful day here in Champaign. A little bit cooler than it has been in the past, but we can deal with that. It's bright and sunny outside. Today, we're going to move on from recursion and begin talking about our next topic, which is sorting algorithms. Sorting is a fascinating problem that maintains a lot of real-world relevance. There's actually new sorting algorithms that are still being developed for certain applications. I saw one posted on Hacker News not too long ago. So this is still an open problem. And sorting is also a great chance for us to bring together some of the things that we've talked about so far in this class. Imperative programming, object-oriented concepts, get to use some of our ideas from interfaces, and it's going to push us forward a little bit in the direction of learning a few new ideas, one of which we'll start presenting at the end of class today. I also want to leave a few minutes at the end of class for us to talk about what we've decided to do about grading this semester and some of the adjustments we're going to make in light of our sudden move online and some of the difficulties in sort of providing help virtually for students. So we'll talk about that toward the end of class. All right, so sorting algorithms, again, sort of bring together a bunch of the things that we've talked about this semester. So this is it's one of the last things we'll talk about this semester. It's a good place to end because, again, it integrates a lot of the things that we've been discussing. So, for example, imperative programming. Our first sorting algorithm that we'll look at together today, which is called insertion sort, as well as a number of different sorting algorithms, take a classic imperative approach in the sense that, they use looping, they use, modifying local variables and stuff like that as a way of providing an iterative solution to the problem of sorting an array of integers. We also get a chance with sorting to learn and practice our abilities to do basic big O analysis. So we're not going to worry too much about being exactly correct, but we're going to try to get things into the right category. And sorting algorithms actually are really interesting in the sense that they provide a lot of fascinating trade-offs. We have sorting algorithms that, in the best case can run quite quickly and in the worst case can run quite poorly. And so this is a place where we actually also get to see the differences between best case, average case, and worst case runtime in a couple of different cases. We're going to look at some recursive sorting algorithms. To the more interesting sorting algorithms we look at, we'll provide an example of doing recursion on arrays, which is something that we talked about was possible on Wednesday, but we haven't really had a chance to do yet. So when we get to implementing merge sort and quick sort, which we will next week, we'll have a chance to practice recursion again in a little bit of a different context. So you guys have been busy writing recursive algorithms on trees, including the last couple of problems that have started to get pretty gnarly. But this is going to give us a chance to look at recursion in a little bit of a different context and also see some runtimes that emerge naturally from recursive solutions to problems. So as we talked about last time, when we looked at search, the binary search algorithm on a binary search tree we said was about O log n, assuming various properties of the tree. When we get to merge sort, we'll see sorting algorithms that achieve O n log n performance. And that's again because they have this property that in each step, they're making the problem about half as small. So sorting, you might wonder, this is really basic problem, right? I mean, is this interesting, right? It turns out that sorting is in many ways a building block. It's a core component of a lot of other algorithms. There's a lot of algorithms that, they start by using sorted data. And so there's this question of how do you sort data initially and then how do you maintain it in the sorted format. So sorting, despite the fact that it's a problem that's very easy to frame and pretty easy to understand, maintains an enormous amount of real-world relevance. Sorting is a problem that people are still trying to solve today. And again, there are still these interesting novel sorting algorithms that people are proposing for certain problems. The sorting algorithm is actually used in Java by default and also in programming languages like Python, was invented not too long ago. I mean, it was in the early aughts. So, sorting is a problem that computer scientists have thought a lot about, but we're still making progress on this problem. People are still coming up with new sorting algorithms to solve certain types of sorting problems, or in the case of timsort, which is something that's used by a couple of mainstream programming languages, this is a general purpose sorting algorithm that exploits features of normal data sets that end up getting sorted. We'll talk a little bit about that in a few classes. So what are some of the problems that we can do better on if we start with sorted data? So searching is a problem that's typically much more efficient if it's performed on sorted data. So go back and think about our phone book analogy. If the entries in a phone book were totally unsorted, it would take forever to find anything, right? You'd literally have to go page by page by page, looking entry by entry by entry, and it ends up being linear time. Because a phone book is sorted, we can perform a log n search. And remember when we went back and looked at our complexity classes, you might think linear time is great, right? But when we look at how fast things grow, logarithmic time starts to become very, very appealing once we get to large number of entries. So again, linear time may not seem so bad, but imagine performing a linear time search for a phone number in an unsorted phone book. That would be awful. And there, the log n starts to make a huge difference. So if we have sorted data, we can perform searches more effectively. Sorting in certain data processing pipelines is used to do things like duplicate detection. So, I was reading a little bit about what it means to be a modern data scientist the other day, and one of the things the article was pointed out is that data scientists, which of course something that all computer scientists are pretty well prepared to do, spend a lot of time working on cleaning and preparing data. This is something known as ETL, extracts, transform, and load. And the idea is that you spend a lot of time, even before you can perform your fancy machine learning algorithms or your statistical computations, just cleaning the data. Making sure because data a lot of times is dirty, it's messy, it's got mistakes in it, it's got duplicates, it's got errors. And so, a good part of working with data is making sure that we're working with good data. Because if you start with bogus data, you can easily draw bogus conclusions. So sorting can be something that can be used. If you have a data set that you don't expect any duplicates in a certain value, you can sort the data by that value, and that very quickly identifies where the duplicates are. And again, sorting is also often used to produce representations of data that make sense to human users. So for example, when I'm looking at a graph of a certain trend over time, let's say the average temperature on the planet over time or something like that, I want to sort the axis on which I present the data so that it's meaningful. I could take the same data set, I could just put the points all over the place, and you wouldn't be able to read it, right? So sorting by time is what allows us to see trends and interesting patterns of data. Now, to try to convince you that this is still something that's going on, this is the page, I think it's called sortingbenchmark.org or sortbenchmark.org. If you Google sort benchmark, you'll be able to find it. This is an annual competition that's held to produce the fastest sorting systems, because this is really not just about algorithms this is about the machines that you run the sorting algorithms on and things like that to perform certain types of sorting problems. And this is a competition that is ongoing. You'll see here that the winners from 2019 are currently posted on this page. It's kind of a fun competition. There's a bunch of different categories, sort of like the Olympics. There's different types of sorting challenges. Okay, so here we go. So there's the amount of time it takes to sort 100 terabytes worth of data. I think there's there's different different categories. Some of them have to do with how long it takes, that are just purely based on speed. Others have to do with how much money it takes. How efficient is your sort in terms of dollars per operation. Some of them have to do. There's a sorting category down here that has to do with how much energy it takes to sort, right? Thinking about the impact that computing has on the planet. This is again something that, and I'm trying to see what some of the latest winners are. So these are the top results. Let's see. This is from 2016, 2019, right? So you see that at least last year in a couple of these categories, these are like the winners for all time. There's a couple of new sorting algorithms and new sorting approaches just from last year where we're still making progress on this problem, right? The sorting algorithm is this competition was originally set up by a famous computer scientist named Jim Gray. Jim Gray, tragically vanished in a sailboat accident or some sort of sailboat. He went out sailing one day in San Francisco Bay and never came back. This was about 13 years ago. There was a really impressive effort by the computer science community and by others that really looked up to him and admired him to try to find him. People went through massive amounts of satellite footage, but until this day, there's been really no sense of what actually happened to him. All right, so we're going to talk about a subset of the sorting algorithms. If you go to wikipedia.com and look for sorting algorithms, you'll find a long page with maybe like 50 different sorting algorithms. We're not going to talk about all of them. We're going to talk about a few. Because if we talked about all of them, we could have an entire semester where we just talked about sorting algorithms. So that's not what we're going to do. We're just going to focus on a couple. Insertion sort, we're going to get started with today. That's our topic for today. Selection sort, there's a few that we're going to have you guys work on in lab next week. That will be the lab activity. Will be to implement and benchmark a few sorting algorithms. Merge sort, actually, we're going to get to on Monday. We're not going to get to today. The slides are a little bit wrong. Heap sort is another version of a sorting algorithm. A quick sort is something we'll talk about next week, probably Monday and Wednesday. And so, there is a bubble sort algorithm. The names of these, are either have to do with something about the way they work or whatever. And so again, there's lots and lots of different ways of solving this problem. And that's one of the things that makes sorting so interesting. You'll also find a couple of really silly sorting algorithms that you can locate on the Wikipedia page. For example, there's one sorting algorithm that just randomly takes all the elements in the array and randomizes it and then checks to see if it's sorted and repeats that process until it is sorted. So it's sort of like if you had monkeys trying to sort something or something like that. And the performance of that algorithm, as you would expect, is pretty bad. So there are still new sorting algorithms that are coming out. So there's something called TimSort, which was released in 2002, that as far as I know is now the standard built-in sorting algorithms used by Java, by Python, by several other mainstream programming languages. TimSort is not a sorting algorithm we're talking about. It's fairly complex, but it builds on and combines concepts from a couple of the sorting algorithms that we will talk about. Okay, so let's get started. So first of all, let me set some sort of common ground rules for our sorting algorithms. One is we're going to sort arrays, and we're going to sort arrays of integers. Now, you might be thinking, well, you told me that if I had two comparable objects, I could sort them, and that's true. We could sort arrays of comparables as well. But just for the sake of simplicity, we're going to assume that our goal is to sort an array containing integers, so we can compare them using the standard comparison operators. Now again, we can generalize our sorting algorithm to sort an array of comparables, and that's something that I think we'll do at some point. But for now, just for simplicity, we're going to sort ints. Okay, so let's look at insertion sort. So insertion sort is our first sorting algorithm, and here's how it works. All right, so given an array of integers, insertion sort proceeds as follows. These are the steps followed by the algorithm. Insertion sort divides the array into two parts. There's a sorted part, which starts out empty, and there's the unsorted part that starts out full with all of the elements in the array. And what insertion sort does is, one at a time, it picks an element from the unsorted part of the array, and it inserts it into the right spot of the sorted part of the array. Now again, we have to do this in a way that keeps the sorted part sorted. So we can pick any element from the unsorted part, but we have to put it into the right spot in the sorted part. Now typically when you implement insertion sort, you choose like the first element from the unsorted part of the array or the last element or something like that. But you could really choose any element. That's not what's important. What's important is that in each step, we move one element from the unsorted part of the array to the sorted part of the array, and we insert it in the right spot. As a result, in every step of the algorithm, the unsorted part of the array gets smaller by one item, and the sorted part of the array gets larger by one item. And as you imagine, if I continue this, if I have n elements in my array, the unsorted part starts with n, the sorted part starts with 0, but in each step I move one element from the unsorted to the sorted, and so eventually, if I run the algorithm for long enough, I move all of the elements from the unsorted part into the sorted part of the array, and the array is sorted. All right, so let's look at one step of this. So imagine that at the beginning, the entire array is unsorted. So here I'm using red to indicate that the array is unsorted. And now what I'm going to do is at each step, I'm going to make the sorted part one item bigger. Now at the beginning, it's very easy because any item I choose will work, right? So in here, I've taken the first item and I've inserted it into the sorted part of the array. I had to do no work to do that because the inserted part was empty. And so any element I put into the sorted part would still be sorted, right? An array with one item is sorted. That's an important sort of thing to establish once we get started as well. So an array with 0 items is sorted, an array with 1 item is sorted. So now my unsorted part has 7 items in it, and my sorted part has 1. Now I need to do a little bit more work. So now my next step is going to be I'm going to take 5 and I'm going to stick it into the sorted part of the array. So you can see over here, now my sorted part has 2 items in it, and my unsorted part has 6 items in it. And you'll also notice that I had to move 5 to the left of 8 in order to maintain the sorted aspect of the sorted part of the array. So now I'm going to repeat this step. Now I'm going to take 7. And I'm moving 7, which used to be in the unsorted part, into the sorted part of the array. 7 has to kind of be inserted in between 5 and 8. 3 is now inserted at the beginning. 4 has to be inserted between 3 and 5. 11 can stay where it is because 11 belongs at the end of the array, the large end of the array. 6 is inserted between 5 and 7, and -1 is inserted all the way back at the beginning. Once I've done this, the array is now sorted. The other thing I should have pointed out, I forgot to say, is that when we sort in this class, we will be sorting in ascending order. That's an arbitrary choice. We could easily be sorting the array in descending order, but we're just going to sort it in ascending order, meaning that the smaller values will be at smaller indices, the larger values will be at larger indices. All right, so, and again, you can see in each step of this algorithm, I've taken an item from the unsorted part and I've inserted it into the sorted part of the array. And so over n steps of the algorithm, the array went from being totally unsorted to being totally sorted. This is insertion sort. So now let's look at kind of a single, well now actually what I'm doing is I'm just showing you kind of where the items end up. So here I took item 8, and item 8, you know, when I go and add the first item into the array, that item can go anywhere because there's only one item, right? 5 ends up having to move in order to be put in the right order in the sorted part of the array. And so you can see that, you know, depending on where it belongs, each element that I move from the unsorted part into the sorted part may end up in a different position relative to where it started. In this case, I'm always taking the leftmost element from the unsorted part of the array, and I'm moving it into the sorted part of the array. And the sorted part of the array is essentially growing from the left to the right. So at the beginning, the sorted part of the array is empty, and at each step, I make it 1 bigger until it reaches the end of the array, and the array is now sorted. So now let's look at a single step, right? So imagine that at this point, I've sorted most of the array, I only have a couple of items left to finish, and I'm looking at what I should do with item 6. So now the question is, how does the insertion work for a single item? I'm taking a single item and I'm inserting it into the sorted part of the array. So let's look at this. So what I'm going to do, and you're going to see this when we implement it in just a minute, is I'm taking item 6 and I'm going to start moving it to the left. And at each step, I'm going to compare it with the item next to it. And if it's smaller than the item next to it, I'm going to swap the two. That's going to essentially move the item 6 to the left, and it's going to move the larger item to the right. And that's what I want, because I want the larger items to go to the right, the smaller items to go to the left. So here, for example, I'm comparing 6 and 11. 6 is smaller than 11, and so I swap the two. Now I'm comparing 6 and 8. 6 is smaller than 8, and so I swap the two. Now I'm comparing 6 and 7. 6 is smaller than 7, so I swap the two. Now I'm comparing 6 and 5. 6 is larger than 5, and so I'm done. I have located the right place in the array, and I can stop and insert 6 into that position. Okay, so one more time, let's go through this. I start by, I'm starting with the item that is the first item in the unsorted part of the array, which is the item at the leftmost portion, but I could choose any item, right? But I'm going to use the item at the leftmost because it kind of works out nicely for this implementation of insertion sort. I compare it with 11. It's smaller than 11. So I swap the two. Now I compare it with 8. It's smaller than 8, so I swap the two. I compare it with 7. It's smaller than 7, so I swap the two. I compare it with 5. it's larger than 5, so I stop, drop it into place, and I'm done. All right, so let's do this. We're going to implement our first sorting algorithm. This is an exciting moment in the class. Let's look at what happens. Okay, and this is tricky, all right? So let's start off by handling some of our quarter cases because we're good defensive programmers. So there's a couple of cases where I don't need to do any work. And those cases are if you pass me a null array, or if the length of the array is less than 2. And why less than 2? Well, if the input array length is 0, it's got no elements, I got no work to do. If the input array length is 1, it doesn't matter what element is in there, it's already sorted. So I only actually need to continue on to the part of my program that does any work if you give me an array that has at least 2 items. So now there are really 2 loops that are involved in implementing this, okay? The first loop, let me go back to my diagram. So the first loop is performing this step. So this is my outer loop. For each iteration in my outer loop, I pick one item from the unsorted part and insert it into the sorted part. Then inside that loop, for each, how do I actually do the insertion? So here's the way I do the insertion, which is that I move the item to the left, comparing it with the item next to it until I find a place where it belongs, and then I drop it in. Okay? So I have 2 loops to write here. So my first loop, the outer loop, that's moving items from the unsorted to the sorted part of the array, I'm going to write that like this. So I'm going to start with the first item in the array, and you'll see why in a sec. I'm starting with the second item, not the first item. I'm going to continue as long as length, and then I plus plus, okay, great. So now I'm going through, what I'm doing here is it's a small optimization. So remember we said that that first item that I insert into the sorted part is trivial because the sorted part, when it starts empty, I can put any item in it. So essentially what I'm doing is I'm starting with the sorted part having 1 item in it, right? Meaning that I'm assuming the sorted part already has an item in it, which is the item in index 0, the first item in the array. Now, so this is going to run, every time. Now what I have to do is actually have to figure out how to move that item from the unsorted part of the array. So I'm going to write this loop, and then we're going to talk about it. So the item that I'm looking at is item I, right? So imagine I have 2 items in my array. I say that the sorted part starts off with 1 item in it, which is the item at index 0, the first item in the array, and the only thing I have to do is look at that second item and decide if I need to swap it with the first item or not. As the array gets bigger, I'm always choosing the first item from the unsorted part of the array. The sorted part of the array is growing from left to right. The unsorted part of the array is shrinking from left to right. So the first item that is not sorted at any loop at any step of the outer loop is the item in index I. Okay. So now what I'm going to do is I'm going to say if input array j minus 1 is greater than input array j. So what is this if statement doing? It's saying if the preceding item, the item at input, so I'm looking at index j for my inner loop. So index j minus 1 is the item before that item in the array. If the item before the item is bigger, then these 2 items are out of order, right? And essentially I need to keep moving that item to the left. So what I'm going to do is if these 2 items are out of order, I'm going to swap them. Now, you might have remembered from like what seems like a long time ago, we talked about how to swap elements in an array. The trick is, well, I need swapping any 2 elements actually. I need a temporary value. So I'm going to set my temporary value equal to input array j minus 1. I'm going to set input array j minus 1 equal to input array j, and then I'm going to set input array, spell, j equal to temp, and now I swap the 2 values, right? So, so now let's see if this actually works, and lo and behold, it does. And I just want to say, I practiced this morning, so I felt pretty good that I was able to get this right. This is a tricky piece of code to write, but you know, let's go through it and look at what's actually happening, right? This is really the tricky part of this piece of code, is this inner loop. But if you look at it, what I've really done is I've just gone through and I've implemented this. So so let's say that in this case, I'm at the point where my outer loop, is equal to 6, right? This array has 8 elements, so this is index 7, this is index 0. So this is the step where I is equal to 6. And the first thing I do is I compare 6 and 5. That's exactly what my algorithm did. And then I compare 5 and 4, and then I compare 4 and 3, and then finally I find the right spot. Now, one thing you might have noticed is that, let's go back to the code, this loop will continue even after it finds, even after this if statement. Like, let's say that I get to the else statement. It actually means that I found the right spot. So what I can do is I can make this slightly more efficient by sticking in a break statement here. Because once I take that item from the unsorted part and insert it into the sorted part, I move it left, I move it left, I move it left. Once I find the right spot, I can stop. Because I know that the part, so once I find the value that is where input array is, input array j minus 1 is not larger than input array j, I know that all of the values to the left are smaller because that whole part of the array is sorted. And so I don't actually need to keep going, right? I can just stop and this will still produce the same result. So let's try a couple of things to make sure that we're actually completely correct here. Let's insert some duplicate values into the array to make sure those end up in the right spot. It seems like they do. Let's put the smallest value way over to the right. Let's put the largest value way over here to the left. It seems to work. Okay. Now let's think about runtime. And this is going to be the fun part of this, or one of the fun parts of this. So first of all, let's look at the outer loop. Remember, whenever we look at runtime, we think about loops, we think about break statements, which we have here. We also want to think about best case, worst case performance. All right, so in this case, the loop, this part of the loop is going to, for an array of size n, this part of the loop is going to execute n times. So I know that my runtime is going to be at least n times something, because I need to think about what's happening in this inner loop. But the outer loop, there's no break in the outer loop. So every step of this outer loop is always going to run. And this makes sense because this outer loop constitutes the process of moving items from the unsorted part into the sorted part. And I know for an array of size n, I have to do that n times. So now the question is, what happens in the inner loop? And what I'm going to suggest is, let's instrument this code a little bit to get a sense of what happens. So what I'm going to do is I'm going to create this value called swaps. And every time I actually swap a value, I'm going to say swaps plus plus, right? And actually, I can really put this in here and get a pretty similar answer, because once I get to the point where this is true, I'm going to break anyway. And then before I return the array, I'm going to print my swaps value. Okay, so now let's experiment. What I'm going to do is I'm going to use the arrays that are the same size, and I'm going to just try a couple of different values and see how it goes. So this is an array of size 8, and it's already sorted, which is what's important to look at. Okay, so here you can see that I actually only ran the inner loop 7 times. All right, so for an array of size 8, this seems like what I've achieved is about ON, right? Okay, what about if I use an array that's sorted backwards? Now I've got 28. Okay, so that's almost 8 times 4, right? It's not 8 times 8. 8 times 8 would be 64, but it's about half that, okay? You'll also notice if I make it 1 bigger, it's growing more quickly than n, right? So the size of my array went from 8 to 9, right, which is an increment of 1, but the number of swaps went up by n, right? It went from 28 to 36. So, okay, so that's interesting. Now, and the reason for this is pretty simple. So let's go back and we're going to look at our insertion sort step, right? So the worst case scenario for this algorithm is that every time it takes a value from the unsorted part of the array, it has to move it all the way to the front of the sorted part of the array. And that's what happens when my array is sorted backwards. So the second step of this algorithm needs to take 7 and ends up having to move 7 in front of 8. And then the third step has to take 6 and yank 6 all the way back to the beginning. The fourth step takes 5 and yanks 5 all the way back to the beginning. And so in this case, my algorithm is doing a lot of work because it has to keep swapping that value and comparing it all the way across the array every time. So what we're looking at here is the worst case behavior of insertion sort seems to be about like O(n) squared over 2. Because, again, if I use 8 values, I'm seeing 28, which is about 32. If I use 9 values, I'm seeing 36, which is about 9 times 4.5, right? 9 times 5. So it's about, so this is growing, again, as I add here, this is growing faster than linear, right? We can definitely tell that. Okay. The best case performance is achieved when that inner loop doesn't have to do anything, when the item is already in the right spot. And that's achieved when the array is already sorted. So insertion sort does extremely well on arrays that are already sorted. So in this case, if I go back and look at my inner loop again, what happens is I pick up the item that I think I pick up the item from the unsorted part, and it turns out it's already in the right spot. So I just drop it immediately and move on. And that's what happens here if I use an array of values that's already sorted. I start with item 1, I pick up item 1, item 1's already in the right spot, I start item 2, I said, okay, is item 1 greater than item 2? No, and so I drop item 2. I go to item 3, is 2 greater than 3? No, so I drop item 3, and just continues. And so in this case, that inner loop does no work. In fact, one thing we can look at, let's put a print statement in here. You'll see that in this case, I never enter that if statement because I never had to do any swaps, actually. Now, if I reverse this and run it backwards, now it gets printed over and over and over again because I end up having to do a lot of swaps. Okay, so let's look at time complexity now based on what we just did. And, when you're getting started, here's one thing I want to make sure that you guys are clear about. When you guys are analyzing algorithms, play around with them. Do a little bit of instrumentation like we just did. Like count the number of times certain things happen. That's totally okay. I was talking to Jeff Erickson, who teaches one of our upper division algorithms courses, and he was saying he's seen a lot of students that when they talk about algorithms in class, they actually implement a simple version of the algorithm in a language like Python or whatever, just to get a feeling for how it works on some simple inputs, and that's totally okay. This is not cheating. You don't being a computer scientist isn't about just being able to stare at some code and automatically divine what happens. Mess around, right? Computers will help you run these type of experiments, and they're very good at it. All right. So worst case we noticed was O(n) squared, and this is if the array is sorted in the wrong order, right? In descending order. Now, depending on how you implemented this algorithm, you might achieve something different. So if we were sorting it in descending order rather than ascending order, this would be our best case, but we're sorted in ascending order. And so when we get an array that's sorted in the wrong order, this produces our worst case runtime because every value has to travel all the way across the array to find the right spot. The best case is if the array is already sorted in the right order. And again, if the array is sorted in ascending order for this implementation, because that's what we were trying to accomplish, if our implementation was sorted in descending order, then the best case would be it being sorted in descending order, and the worst case would be ascending order, right? Average case, for insertion sort is typically listed as O(n) squared. And again, this really ends up having to do with the features of your data. One of the things that it turns out in practice is that, and this is something that Tim's sort, that advanced sorting algorithm that I mentioned a little bit earlier, takes advantage of, is that in the real world, a lot of data that gets fed into sorting algorithms is almost already sorted. So a lot of times what you're doing is you're taking data, you had one new value and you're resorting the data, so most of it's already sorted and there's just one new value you're trying to fit in. Or you're taking two pieces of data, two data sets that you got from two different places that might already be sorted, and you're merging them together. And so and TimSort actually tries to take advantage of this, and that's actually one of the ways that it runs so fast, right? Is that it uses the fact that in a lot of cases, large chunks of the data that sorting algorithms run on is already sorted. It's very rare to actually feed a sorting algorithm data that's completely random. That's just not very common. All right. Now, the other thing we're going to look at with sorting algorithms, because there are some trade-offs in this space, is we're going to look at how much space or memory does it actually use. So in this case, we're seeing that our sorting algorithm, so we go back and we look at, how much, did we have to create an extra array? No, we didn't have to allocate an extra array. All we needed was this one, I have this swaps variable that I can get rid of now. If I go back to I can actually set up my temporary variable here and then just use it inside the array. And so, it's mad about this. So I essentially, all I need is this one temporary variable. All the rest of the work is being done inside the array by moving values around. And this is something else that's sort of appealing about insertion sort. This idea that I can do it in place is sometimes how it's referred to, without needing any extra space. Okay, awesome. Great. So this is the table, the beginning of a table that we're going to start to build up over the next couple classes. And this is going to give us a chance to compare insertion sort to somewhat more sophisticated approaches like merge sort, like quick sort, and look at the trade-offs there, right? But this is our starting point. Now, insertion sort's worst case runtime is O(n) squared. And this is a clear sign that we can do better, because you can prove, and maybe you actually do this in one of your later courses, but you can prove that for any sorting algorithm that's not a bad sorting algorithm, remember, you can always come up with a bad algorithm to do things that's slower than it needs to be. But an optimal sorting algorithm, the worst case should be no worse than O(n) log n. And we can also show that in the best case, it should be close to O(n). So these are things that we can prove that the worst case behavior of an optimal sorting algorithm is O(n) log n. And there's a number of sorting algorithms that accomplish that. But we can also show that in most cases, our performance should be close to O(n). Now, insertion sort clearly doesn't meet these criteria because its worst case performance is O(n) squared. Okay, so I'm going to take about 5 minutes and do a brief digression into Java generics, and then I'm going to talk a little bit about the decisions we've made about grading for class. All right, so one of the things, this is here because we're going to start using this feature in a little bit, so I want to start kind of like, letting it sink into your brain. So when we use lists, one of the things, lists were this incredibly useful data structure. You guys have implemented them, and then you're now using them on several homework problems. Here's one of the problems with Java's built-in lists, and you may or may not have noticed this. You may have seen some warning messages on the homework or something like that. And so here's how we've been using lists, and I think you might have used them a little bit differently on the MP, but just bear with me because I want to kind of try to explain exactly what's going on here. So when you create what's sometimes known to as a bare list in Java, this is a bare list, and you'll see why it's called a bare list in a minute. A bare list, the good thing about it is that a bare list can store anything, right? It can store any Java object. The bad thing about a bare list is that it can store any Java object. And so what happens when you insert things into a bare list is that they are upcast to a Java object. Remember casting? I can automatically upcast any object in Java to capital O object because they all inherit from capital O object. The problem comes when you try to get things out of the list. So here, everything seems great. I added a string to my list, but now what happens is when I call list.get to get the first element, this is going to produce a compiler error because what I'm trying to do is I'm taking something that was converted to an object reference and I'm trying to use it as a string reference. So I can use an explicit cast to convert this to a string. And then everything will be hunky-dory, except if, whoops, I add an int to my array or to my list, and now I have a problem, right? Now I'm having, I actually have a class cast exception on line 10 because the thing that I was putting into my list, I put something into my list that was an int, and then I tried to cast it to a string, right? So this brings us back to this discussion we had very early in the semester about compiler errors versus runtime errors. So Java and many languages after it have tried to convert errors that might occur at runtime. We want them to happen when we compile our code. And the reason is compilation is something you have to do before you can even run and ship your code. And so any error that you can catch at that point that does not become a runtime error means one fewer crashes that your actual users or clients are going to experience. Okay, so catching, the more the compiler can do for you, the better. Now, here's the problem with this list. Typically when we use lists, we're going to use them for a certain type of data. We're going to put strings into our list, or we're just going to put integers. But when you use a bare list in Java, you're not telling the compiler anything about what you're doing with the list. You're just saying, give me a list that can store any object. Then it's up to you to keep track of what kind of objects are in that list. A better way to go about this is for you to tell the compiler, for you to tell Java what type of object you're going to put in your list. And here's how we do that. This uses some new notation. It's these angle brackets. And this is something that's referred to as Java generics. So what this allows us to do, and we're actually going to do some programming with Java generics in a few weeks, but for now we're just going to look at how to use it. It allows us to use these containers that can store any object, but we can also tell the compiler what we're doing with them, so the compiler can check to help us make sure that we're using that list safely. So here's an example. So this line of code is declaring a list of integers. So what's inside this angle bracket is the type of object that's going to go into this list. So now what I'm doing is, I'm not just saying I have a list, I'm telling Java this list is going to store integers. And then I have the name of the list, and over here I need to use the same kind of syntax. Technically I actually don't, I'll show you a shortcut. But now this says I'm creating an array list, but this array list isn't just going to store any Java object, this array list is going to store integers. And so now what's cool about this, and I've got to fix this example up here, is that the Java will check and help us because it knows what I'm supposed to put in the list. So here what I'm doing is I'm creating a list of strings. This is what's sometimes known as the diamond operator. So I can put the type over here on the right, or I can just omit the type, and what Java will do is it'll use the type from the left side of the expression. So this says I'm creating a reference variable called list that's going to refer to a list of strings. And on the right side, I'm assigning it to refer to a new array list. So this is my implementation of list. And that array list, because I'm using this empty diamond operator, is also going to be an array list of strings. So the nice thing about this is I don't have to do this downcast. So you see on line 10, this code will compile without a problem. The other nice thing about it is that Java will help me make sure that all I put into that list are strings. So here I'm adding something that's an integer. Now, and I can do something like system.out.println s.length, just so I can prove to you that this is actually a list of strings. So when I use a generic list in Java and I provide a type, I don't have to do this unsafe downcast when I take the item out of the list. And the compiler will also help to make sure that I don't put objects into that list that violate the type of list that I told Java it was. So here I said list is a list of strings. Java is going to prevent me from adding an integer to a list of strings. Okay, so this is all for now about generics. Again, we will come back and talk about this. We're actually going to show you towards the end of class how to use generics in your own code, and that's great preparation for some of the things you'll see later on, particularly in 225. All right, so I've got 5 minutes. What I want to do here is just pause and announce kind of what we've decided to do about grading this semester. So, it was like, I think, 3 weeks ago now that we came back from spring break. Then that feels like a long, it was in fact, looks like he was maybe even longer than that, but anyway, I mean, we've been back for a while now. And yeah, this is the end of the third week since break. And when we returned for break, we talked a little bit about how the rest of the semester was going to go. And what I said is that if there was an option to move the course to pass, no pass, I was going to do it. And since then, what has happened is, unfortunately, we did move forward with an application for pass, no pass, and it has just taken too long to get through the system. It's still, we're still haggling with the university about this. They have made it very clear that they don't want courses to apply pass, no pass. They've put together a very slow and uncertain system for doing that. It's already dragged on for 3 weeks. During that time period, I really haven't been able to talk to you about it. They've told instructors that they're not allowed to talk about the fact that they applied for pass, no pass, which I think is ridiculous. And so the main reason that I wanted to do that was because I wanted to provide you all with some relief, with some reduced anxiety and concern about your grade in the class. And unfortunately, due to the actions of the university, I haven't been able to do that. 3 weeks have gone by. We're almost to the end of the last MP checkpoint. You guys have still been working your butts off on the homework and on the quizzes and things like that. And so at this point, my fear is that if we actually continue to go forward with the pass, no pass application, what would end up happening is it might not be approved till like the last week of class, or maybe even May. And so you would have done all the work and had to worry about your grade, about how you were doing in the class. Many of you were doing very well. But continue to worry about that until the last day, and then I'm gonna be like, no, you can't get that A or that A minus that you earned because finally this pass, no pass application goes through. So what I've decided to do is not go forward with the pass, no pass application. So we will provide letter grades for students this semester. We're making a couple of changes, however, to try and just sort of reduce the stress and anxiety around this process. These changes are on the syllabus on the website, but just let me walk through them with you. So one change is that we've increased the number of drops for both the MP. So there's now 1 MP drop. We have increased the number of drops on the quizzes from 2 to 3, and on the homework from 8 to 12. This is designed to accommodate, some of the struggles that many of you have had sort of like moving back from the university where you had good Wi-Fi and you had a schedule and stuff like that, and going home and having to deal with, bad internet and additional responsibilities that you might have around the house, helping your parents or whatever, and just the stress and anxiety that's surrounding us right now due to this crisis that we're living through. So that's one thing. The second thing is that we are going to, we're going to assign letter grades. The cutoffs that we use to do that are going to be made with consideration of what's going on around us, right? I suspect that we're not going to have to make huge adjustments. Typically, students in this class do quite well. All of you are on track. I just looked at the grades this morning to do extremely well. I think it looks like about 70% of the people in the class are, in the A grade range at this point. But we will certainly, when we actually sit down to figure out exactly where those cutoffs are, we're going to be generous, and that's going to be done with consideration of what's been happening. The third thing is that in the past, I've waited quite long to release exactly, or to start publishing the letter grades through our grading site. This semester, my plan is to push that up earlier with the intention of making sure that people who are deciding about credit, no credit, will have some sense, not a perfect sense, because there'll still be a few assessments that we need to finish, but some sense of what your final grade would be before you made that decision, or at least like what the grading boundaries are. So we'll probably publish those, towards the end of April, but certainly before the deadline to apply for credit, no credit. From here on out, so let me just talk about the next few weeks of the semester, because we don't have a huge amount of time left. MP4 is out. People, have been working on it. We're going to continue to try to help people this weekend. That's going to come in over the weekend. Once you get through the MP4 checkpoint, you have 3 weeks to work on the final project. The final project grading has been, and will continue to be extremely generous. I do want you to do the final project. It's a huge opportunity and it's a really great learning experience, but we have always been extremely lenient with what we will accept for a final project, and we will continue to do that. So I expect that most or all of you are going to get those 10 points without a problem. Other than that, we're going to move forward with the way we have been. At this point in the semester, kind of once we get past MP4, there's kind of a sigh of relief. You know, you finish the MP, the final project is generous and lenient. The homeworks are getting more difficult, but that's okay because you'll have more time because the MP is off the table. The homework drops, some of those extra homework drops I hope will help. And so that's our plan. I'm certainly open to, continued conversation about this, but I just wanted to make sure you guys understood that the course will use letter grading this semester. And again, I really apologize for all the uncertainty about this. That's been a source of stress for me. I know it's been a source of stress for some of you that have been worried about which way we're going to go with this. All I can say is that as an instructor, I'm extremely frustrated about how this was handled by the university. The CS department has done a fantastic job of working with instructors, but the entire university has been very slow and very halting to move forward with this plan. And to me, that really ends up, in many ways, reducing what should have been the benefit of it, which is reduced stress and anxiety for the students in this class and in other courses. So that's our plan. Again, if you have feedback or comments on that, you can certainly contact me over email, message me on the forum, post on the forum if you want to have a conversation about this with other people, but this is our current plan. Wish you guys the best of luck wrapping up with the MP. Oh, one more important announcement. So we have finally, and again, I apologize for the delay here, made some tweaks to our office hours scheduling. It took us a little time to kind of get everybody back on the same page together. Starting today, we are going to run an 8 to 10 a.m. office hour block, which is designed to accommodate some of the people that are not in the central time zone anymore. We will then do another 6 hours of office hours from 2 p.m. to 8 p.m. So instead of running from 12 to 8 p.m., we're going to do 8 to 10 a.m. and then 2 to 8 p.m. Please be patient with the staff during this time. We are really doing the best that we can to try to help. The staff have been dispersed all over the place. Their lives have been disrupted by this. Normally, in a good semester, CS 125 relies a large amount on our volunteer course staff and CAs to help out with things. A lot of them aren't in a position to do that, and they're stressed out about other stuff. So we're doing the best we can. There are some fantastic people that have been doing a great job helping you guys out on the forum, on the new help system, over Zoom or whatever. We're going to continue to do that. I wish you guys all the best of luck wrapping up MP4. Have a wonderful weekend. We'll be back here to talk more about sorting algorithms on Monday. See you then.